Hi, everyone. I am Aleena Taufiq, a principal engineer at Verizon. I'm currently working on the Future Tech R&D team, which is just a fancy way to say that any of the buzzwords that come out in industry, my team gets to look at them, evaluate them, and see if there's potential for Verizon. And since I am a data scientist, anything that's related to AI or machine learning, that comes my way. And so for the past year, I've had the opportunity to work on what I think is the coolest new tech related to AI, and that is quantum machine learning. Although I do know that generative AI is a huge deal right now as well, just an FYI, some of the images in my presentation were actually generated by Stable Diffusion, so I kind of feel like I have a nice 50-50 hybrid type presentation. Another, I guess, FYI is that QML is a very, very dense topic, but I'm gonna try and make it as fun and exciting as possible. So just bear with me if there's something a little too technical. I promise I'll try to explain it really well. So first off, a lot of you are probably wondering what QML is, and what it is the cross between quantum computing and machine learning. So when you use quantum computing on machine learning applications, you can potentially get a quantum speedup or improved solution quality of your machine learning applications. There's a lot of potential benefit in the area. Recent research has actually shown that there is practical advantage when you apply quantum computing to machine learning applications. They've proven, or they've shown practical improvements in solution accuracy as well. So because of all that, because of all of the recent and rapid development of quantum computing and potential applications in the machine learning domain, quantum machine learning was a very, very exciting area for us to get in on the ground floor and kind of evaluate for our own uses as well. There have been many advancements over the past 12 months. There's going to be plenty of more advancements in the future as well. So a very, very exciting new tech area. And based on the research that I conducted over the past year, I found that we can expect to see some small-scale production applications within the next 3 years. So a very exciting space and a very interesting space to learn about as well. So there are 3 quantum phenomenon that can prove to have some sort of benefits using QML algorithms and QML applications. The first one is quantum parallelism. So quantum parallelism allows you to perform multiple calculations in parallel, allowing you to get a potential speed up. The second quantum phenomenon is quantum superposition. And superposition is when a particle can exist in multiple states simultaneously. And this enables the ability to explore more possible solutions, which could potentially lead to more efficient solutions and more accurate solutions as well. The third quantum phenomenon is quantum entanglement. Quantum entanglement is when 2 particles are linked and the state of one of the particles affects the state of the other particle, regardless of the distance and space between them. This quantum phenomenon actually allows quantum computers to perform operations that wouldn't be possible classically. So this could potentially allow for your QML algorithms to perform tasks more efficiently than their classical counterparts. So when conducting my research in QML, it was really easy for me to classify and categorize the research done in QML into 3 different categories. Note that this is a taxonomy that we created on our own. This is not an industry standard. This is not the next big quantum industry standard or anything like that. But the 3 focus areas that were easy to divide different QML algorithms into were quantum accelerated AI, machine learning as an approximation of quantum circuits, and integrating quantum elements into classical topologies. And each of these 3 focus areas actually have different applications and a different timeline of when these will actually become practical. So the first focus area of QML, quantum accelerated AI, is actually currently the most practical. This is currently being done today, and what it is that you take your classical topology and you replace the optimizers that minimize the loss function in those topologies with quantum algorithms. And this is currently being applied and evaluated across multiple different industries, one of them being the Q-means algorithm being evaluated in the medical industry. So there was a paper released where they used a quantum Q-means algorithm, which used quantum subroutines and a quantum swap test for distance calculation. And they were actually able to get a quantum speedup and more accurate results as well. So there's a lot of potential in this area. It's currently the most useful at this point in time. Another example of this would be quantum SVMs. That's currently being used in the drug discovery domain. So the second focus area of QML is currently the most specialized for, I guess, optimization specifically. So machine learning as an approximation of quantum circuits samples small circuits multiple times using a machine learning algorithm. An example of this is the category of VQAs, variational quantum algorithms. And what that does is it uses a classical optimizer to optimize to train parameterized quantum circuits. It's used in the optimization space. And within VQAs, you actually have the QAOA algorithm, which stands for quantum approximation optimization algorithm. And it's a hybrid quantum classical approach for combinatorial optimization. Another example is the VQEs, which are variational quantum eigensolvers, which is the quantum way of calculating eigensolvers. And this currently has applications in the chemistry industry. I'm not currently in the chemistry industry. I'm not currently working in optimization, but this was definitely an interesting area to learn about. And the third focus area, which I think is the most exciting, is integrating quantum elements into classical topologies. I'll go a little bit into detail why this is the most interesting focus area to me. But this focus area replaces elements of a classical topology with a quantum circuit. So if you have a neural network, you replace one of the layers of that neural network with a quantum layer. And this is currently limited because of limited qubit capacity and hardware limitations and all of that fun stuff. But it can be used on one-dimensional time series analysis, and examples of it are quantum convolutional neural networks and quantum Fourier transforms. As part of my research, I actually conducted a POC using a quantum convolutional neural network, which I'll talk a little bit about towards the end of this presentation. But there's a lot of exciting stuff going on in that space. So I've talked about what QML is. I've talked about the focus areas and things like that. But whenever I mentioned quantum to anyone I've spoken to at this conference over the past 2 days, everyone looks at me and says, quantum's not a thing right now. And it won't be. I don't understand why you're looking into it. I don't understand. One of the most fun conversations I had was with someone who said, quantum is a bunch of nonsense and it's never going to have any applications. Well, that person was wrong. Quantum, QML specifically, is being evaluated in many industries at many, many companies. And companies have actually shown a lot of potential benefit using quantum. And I'm actually going to give you guys a snapshot of a couple of different use cases and a couple of different companies that are currently evaluating, implementing, or using quantum. And actually, some of the people who work at some of these companies might be in the room. So I apologize if I completely misrepresent all the work you've done, but I'll try to do a good job. So This is an industry overview. Again, this is only 5 of the many, many, many industries that are evaluating quantum. And under that are companies within those industries. Again, a very small snapshot of what's actually going on. So in the natural science industry, you have Argonne National Laboratories predicting the properties of complex materials. In the chemistry industry, you have Menton AI that's using QML and quantum SVMs for drug discovery and protein discovery. In the energy industry, you have Siemens using knowledge graphs and QML for anomaly detection. In finance, one of the biggest leaders is JP Morgan Chase. I actually met a few people from JP Morgan a couple days ago, so we're going to focus a little more on them. They have an entire future lab for applied research and engineering, and they're using and evaluating quantum technologies and asset pricing, financial forecasting, stock selection, and so much more. There was a paper actually that they released a couple years ago that was like 50 pages long with all the things that they're looking at. In the automotive industry, Hyundai has actually partnered with IonQ, which is a quantum company, to evaluate the use of their technologies and apply it to specific use cases at Hyundai. And one of those is traffic sign detection. This was one of the big pieces of quantum news that came out in the past 6 months. So there's a lot of stuff going on. This is only, again, a very, very small snapshot. Oh, and then on top of that, you have the person at Verizon also looking into QML. So obviously this is being applied across multiple industries, very exciting, and it was very exciting to be able to get into this on the ground floor and kind of build that foundation of knowledge for not only Verizon, but also getting to share that with all of you. So I've talked about who's using it, how it's being used, but now I'll talk a little bit about a couple of the algorithms that I thought were interesting and some of the main libraries. So if you guys want to go test out and get your hands dirty on QML by yourselves after this presentation, you'll have the means to do so. You'll know where to go and what to potentially use. So again, this is a small snapshot of some of the super interesting quantum QML algorithms. The first one is the QCNN, which I'll talk about a lot more later. And it's currently being used for image classification, has shown a potential improved solution quality. Very, very exciting stuff. The Q-means algorithm, I talked about being evaluated in the medical industry, but it's also being evaluated in the energy industry as well, and has shown a potential speed increase. Quantum Fourier transforms are being evaluated and used in finance, and has shown potential speed increases as well. And then quantum SVMs, I also touched on a little bit in the drug discovery domain, and they've shown a potential speed increase and improved solution quality. So these are a couple of the algorithms that I thought were particularly interesting whenever I was conducting my research. And there are some potential use cases that you guys could potentially look into using these algorithms as well. These are some of the very popular libraries that you can use for quantum machine learning. The first one being Qiskit machine learning. You can't talk to anyone about quantum without them mentioning Qiskit. So Qiskit machine learning is a QML library. It defines a generic interface for quantum neural networks. It currently only integrates with PyTorch, but the plan for them is to connect with other packages as well in the future. I personally did not use Qiskit for my POC. I actually used the next one, PennyLane. And PennyLane, what that allowed me to do was to run my QCNN the way that I would run a normal neural network. So it was very helpful for me in that case. It integrates with quantum hardware, PyTorch, TensorFlow, all that good stuff. Then you have TensorFlow Quantum, which is another very popular library focused on rapid prototyping. And then the last one on this list, again, this list is not exhaustive. There are plenty of libraries you can use to explore, but the last one on this list is Lambec. This is actually the world's first open source quantum natural language processing toolkit. It was released by Quantinium and Honeywell early last year, And the goal of it was to improve and speed up the development of QNLP applications. It's currently in the very early stages, currently only being used for small-scale experimentation, but they also have a very rapid development schedule, so we may see some improvement in the future, in the near future here as well. So I have mentioned my POC multiple times. I've gotten you guys all excited about hearing about something we did in QML that was very exciting. So now I'll talk a little bit about that. So recently, a lot of researchers have released papers saying that QML has shown a potential improved solution quality. And one particular example of this was released by Baylor University last year as well. They said that they created a QCNN, a quantum convolutional neural network, that outperformed a classical CNN and was better fit to hold up against adversarial attacks. And this was very interesting. So what I wanted to do was I wanted to replicate these results and see if I could take it a step further. So what I did was I replicated the results by creating our own QCNN on MNIST data, which was used in the paper. And then I also used that QCNN on resized images as well to see how well the quantum algorithm would perform in noisy circumstances. So what a convolutional neural network is that it's very, very similar to a classical CNN, but whenever you take your pixels, you put them through a quantum circuit, throw some rotations on top of that, apply a unitary, which is just a mathematical operator to preserve the length and angles between different vectors, obtain a measurement value, and then map those values out to different output channels, and you iterate over that again and again and again until you have your output image. This is how we set up the model. I used penny lane for the quantum processing. I used TensorFlow and Keras, and then I tested on a very, very small data set. The training set was only 50 images, the test set was 30, and then I resized the images. And then I set up the quantum circuit with a very small quantum circuit using 4 qubits on a quantum simulator using penny lane. And then the images went through the convolution layer, quantum preprocessing, and then I actually took classical images and the quantum preprocessed images, sent them through a neural network, and got results and validated and compared them. This is what the quantum preprocessing looks like. So basically what we did was we took a quantum pooling layer and put it into our QCNN. And this is what the input and output looked like. And so you can see the encoding, the circuit, the decoding all took place on the qubit or on the quantum device. This is what our sample looked like with the full-sized and the resized images. And then seeing this, obviously you can see that the resized images were severely degraded, but we got some very interesting results. So if you look at the left-hand side, these are our results using full-sized images. And you can see that the quantum layer and the classical model both actually converge to the same point, the same accuracy. But whenever you take the resized images, the quantum layer model actually outperforms the classical layer model. And we understand that a 40% accuracy is not good, definitely not useful for production applications. But you can see that when you add a certain level of noise to images, when you severely degrade these images, you can potentially get an improved solution quality using a quantum layer, which was particularly interesting. And this actually led to more questions. I was able to test on Gaussian noise and added random noise, and I was able to show that this was pretty consistent across the 3 different tests that I did. Obviously, 3 tests is not enough to make a big announcement that I discovered something new in quantum, but it shows promise. You can see that the quantum layer actually outperformed the classical layer whenever there was any kind of noise. And that was very, very exciting. And so the results indicated a possible quantum advantage, and that actually led to more questions, more opportunities, the potential to test on quantum hardware, test more noise models, apply this this method to different use cases as well. And then it also affirmed our interest in QML. It reaffirmed that QML is one of the most exciting technologies, and it's a very exciting time to be a part of the tech. And it's definitely an area where it shows promise and a lot of potential benefit in the future. And that is all I have for you guys today. Thank you.